I should start by giving you some background. So I am from the machine learning group at Microsoft Research Cambridge, and you might be wondering what am I doing here, right? So essentially, around 3 years back, so my background is in sort of operations research and optimization problems. And 3 years back, Yoram basically joined the lab, and we started collaborating on a lot of like game theory models, right? How do you find the maximum utility coalition and so on? And then at some point we realized, oh, we should really test out what these models actually do. I mean, whether people react or play as we expect them to do in these models. And that started a whole line of research on behavioral experiments, and that's what I'm going to talk about. So this is joint work with a lot of people, a number of people, including Yoram, Thora Grapel, who is another person in the machine learning group, Gavin Smith, Mike Armstrong, David Stilwell, Michael Kearns, and Ralph Herbrick. So let me start by giving you a motivation. So why is sort of Microsoft interested in this? And so we considered a very sort of toy market model, right? So suppose you have a market for cloud computing, right? And in this market, people are willing to sell what you sell in a cloud computing market, computing resources, right? Maybe clusters of different computers. So there are, suppose, 3 vendors in this market, Bob, John, and Alice, and they have a different amount of resources. So Bob has 4 sort of computers to share, John has 4 again, and Alice has 2. Now suppose a customer comes in, right? A customer, Charlie, comes in and says, I want 6 machines, and I can pay $100 for these 6 machines, for using them for 1 day, right? Now the question could be, how do you basically, which vendors should collaborate, and then how should they split the reward? Now, so that's the central question, right? How should the vendors come together and distribute the $100 among themselves? Right? So you can sort of expect that because vendor 3 has half the number of units as vendor 1 and vendor 2, vendor 3 should basically get a lower number of a lower share in the $100, right? But if you basically think about, if you just ignore for the moment that there is any opportunity cost, right? Suppose electricity is coming for free, and vendor 2 and vendor 1 could not gain anything by leaving their computers not used, then all 3 vendors have equal power in some sense, right? Vendor 1, vendor 3, any team from 1, 3, 2, 3, or 1, 2 can basically fulfill the demand, right? In some sense, they have equal power in this sort of game. And this sort of situation appears in many sort of contexts, right? So suppose you have a parliamentary democracy and there are 3 political parties. One party has 4 MPs, the second party has 4 MPs, and the third party has only 2 MPs, right? So again, if you require 6 MPs to form the government, all parties have the same number, the same power, right, in some sense. And how should the coalition partners divide up the political power? So these games are essentially called weighted voting games, right, where there are a set of agents, and each agent has this resource Wi, right. So in the case of the political parties, it was agent 1 had 4 member of parliaments, agent 2 had 4 number of parliaments, and agent 3 had 2 member of parliaments, right. And the objective of the game is basically to form a coalition such that when you sum up the weights, you are greater than some threshold. And in the previous case, the threshold was 6, right. So in a weighted voting game, the question now arises, how do people sort of distribute the payoff when they win the game, right? And of course, as Yoram sort of alluded to yesterday, there are notions of fairness which people have used, and one such notion is the Shapley value, right? So I'm not going to go into the details of why this is a fair sort of metric, because I mean all of you probably know about this, and Yoram already discussed this yesterday. So the question that we asked is, do people use Shapley, right? Do people play Shapley? So Shapley gives you a way of saying this is your power and this is the way you should, this is the proportion in which you should distribute the payoff, but do people actually follow that principle? So to sort of answer that question, we ran a set of experiments. And this was published in AMAS last year. So we created this game called Rip-Off, in which there were 5 players, and each player had a weight, right? This 0.25. They could negotiate the payments that they want. So in this case, the person is saying, I want the full payment. I want the full, I want the 100% of the payoff, right? The fraction of payoff that they want, and then they can form and they can basically join different teams, right? So this is a weighted voting game where the target, the threshold value was 1. So agents had to come together to reach their weight 1, and their share, when you sum up the shares, it should be less than 1. Right? That was essentially what the agents were trying to do. So this is just one player, but they had access to actually, they could see the weights and what the different, all the other 4 agents were asking for, right? So this is player 1, this is player 2, this is player 3, this is player 4, this is player 5. Player 1 can see their choices, right? They can just change 2 things, the share and the team. Right, which team they want to belong in and what fraction of the money they want, right, to belong to that team, right?
Only one team here.
There could be multiple teams, right? So agent 1 is belonging to team 1 at the moment. Yeah. So essentially now different agents can join different teams, and they can basically join the same team, and a team wins if the total weight of agents in that team is greater than 1. And the total share is less than 1, right? So that's so this is the game. So now this is a weighted voting game, and you can compute.
One team?
Hmm?
You can only join one team.
You can only join one team. You can choose your team essentially, and this is like you can choose your team dynamically, right? So now this is a weighted voting game, and the distributions of payoffs one would expect sort of match up to the Shapley value. So this is, or are people rational, or are not are people playing some completely irrational sort of stuff. So we ran this experiment with 30 people recruited from MSR Cambridge, and it was sort of a really tough job. I mean, we sat down and in these sessions, which are 2 hour long, and then we made people 5 groups of people play this game, right? And this was over many days, right? And this is the set of results we got. So on the x-axis, you see the Shapley value of that player, and on the y-axis, you see the actual proportion of the payoff that they actually took out of the game. So you saw that it was roughly sort of proportional, right? So we thought, okay, that's great. Agents are playing, people are playing Shapley. There were some deviations, but I mean not a lot. So that sort of led us to this question that we spent such a long time, like this was ages, like this was like 1 month of effort trying to run these very simple experiments, right? And it was only with 30 people, right? So it was a biased population, and it took a lot of time. So can we do something better? So this is not just a situation in the rip-off experiment. This is a general situation that happens in behavioral game theoretic experiments, right? You have a lab environment where you invite subjects into the lab, and the experiments are small scale. They are expensive because generally the incentive use is monetary. You have to pay people to actually take part in these games. It's time consuming for the person who is actually running the test, and there is a lot of subject bias, right? Because you are recruiting these people from universities or your own departments, like in MSR Cambridge. So essentially, what we wanted to do is not go beyond the lab environment and go into the online crowd, right? So instead of those 4 sort of people who we invited, we wanted to go to the online crowd. So what are the benefits of and the online crowd that we decided to sort of tap is people who were on Facebook. So what are the limitations of the lab environment, right? There are only a handful of subjects. It is artificial lab setting, and of course, there is a well-known weird bias which Henrik and others have sort of written about, that most subjects in these studies come from westernized educated people from industrialized rich democracies, right? So you cannot, if you are running an experiment with undergrad at Harvard or MIT, you probably cannot generalize the results to somebody in a village in South Africa or India or China, right?
Is there actually evidence to suggest that people are?
So, for example, the ultimatum game, right? So people have run ultimatum games in different sort of continents, different countries, and the results are completely different, right? The rejection threshold, the point at which people sort of reject the offers is very different in different countries, in different societies, right? So there are cultural differences. In some countries, it's fine to have unequal payoffs. In other countries, it's not, right? Now, in the case of Facebook, you have 800 million people, 800 million subjects on Facebook, potential subjects on Facebook in their natural environment from all over the world, and can we use them for behavioral research, right? That's the question we were asking ourselves. So to test this to answer this question, we looked at a particular type of games called Blotto games. Now, I'm not sure how many of you know about Blotto games, so I'll just give you a quick introduction. So essentially, in a kernel Blotto game, you have a set of battlefields, right? And you have two opposing armies, right? So each side has to sort of distribute 100. Suppose you are given a set of soldiers, 100. Each side is given 100 soldiers, and they have to distribute these soldiers in the 5 battlefields, right? So say they were red and blue were the two different armies. Red distributed them in a uniform order, and blue sort of concentrated all the troops in just one battlefield. So the side with more soldiers in a battlefield wins that battle, right? And in this case, red wins against blue. Red wins 4 battlefields, and blue wins only 1, right? So there are 2 formulations of the game. One is a majority formulation where you look at which team has won the majority of the battlefields, and the other is a plurality version of the game where you actually count the number of battlefields that are won as well, right? And this is a general this is sort of a type of a multi-dimensional resource allocation game, right? And it has been sort of used to model many different situations. For example, 2 presidential candidates, right, trying to distribute money, add money in the 50 states in the US, or the amount of time they have. So starting today, there are like 6 months left. How would the 2 candidates distribute time among the different states, right? With the constraint that they really want to outspend their opponent in the majority of the states, right? And it could also be the case to model the advertising scenario where 2 companies, Pepsi and Coca-Cola, are basically fighting for 5 different markets like South America, North America, and they have some fixed budget, $100 million. How would they spend it on these 5 different markets? So there has been a lot of this game has a long history, like 80-year-old history, and there are theoretical results. People know that the optimal strategy for a general game with M troops and N battlefields in the plurality version of the game is to have a randomized strategy which allocates troops to the battlefield symmetrically, in the sense that if you marginalize over all possible runs of that strategy, you should get a marginal distribution for each field, which is in the range 0 to 2m divided by n. So m is the number of troops, which is in our case 100, and n is the number of battlefields, which in our case is 5. So between the range 0 to 40, right? So essentially, when you marginalize through all strategies at each field you should get 0 to 40, a uniform distribution between 0 to 40. So this is the theoretical optimal way to play the plurality version of the game. So there have been previous experimental evaluations to see whether people actually play the game in this way. So rather than Rubenstein, they took subjects who were newspaper readers. They basically launched this game in a newspaper and then asked people to sort of play this to submit strategies. And then they also did experiments where students who were taking game theory classes in different universities were asked to give one strategy to play this game. And then they saw which strategies were performing better. So this is only a one-shot game, right? They only use one strategy per user. And then there has also been a work by Chaudhary and others, which just uses 128 Purdue students and to do these experiments. So I'll now talk about what we did, right? So we launched this app called MSR Project Waterloo on Facebook roughly 2 years ago now. And so essentially the game worked like this. So this is the introduction screen. You can play a random game, play a game against a stranger, a hidden player who you don't really know, play a game against your friend, or play a game against a stranger who has played the game before, right? So if you say you want to play a game, so you can challenge a stranger or you can challenge a friend. And then once you have decided who you are challenging, you distribute your troops. You allocate your troops to the different battlefields. The other player also does that, and then you get the final result, right? And then you see whether you have won the game or not, right? So very simple dynamics, right? It's a very simple sort of implementation of the game. So in previous experimental studies, and this is sort of generally true for many behavioral game theoretic experiments, the incentive is monetary. People are told that you will basically earn money based on the performance in the game. Now, if you really want to scale up to 1 million people or a large set of people, monetary incentives don't scale up, right? You cannot spend $100,000 for basically somebody playing 10,000 games, right? Yeah.
So it's possible to use lottery tickets. I mean, I can pick the size of $1,000 and then you win lottery.
Yeah, so you can have a lottery type system, but then you are again introducing a bias, right? Some people might not be interested in playing the lottery, right? Or they might have different notions of what it means. So some people are risk averse. They will say, oh.
Yeah, but also for money, you have different willingness to step in the game because you are richer. So I think
yeah, so that is true. There are scaling measures. So you can use monetary incentives which sort of scale up by using a lottery mechanism. We sort of looked at the other sort of incentive mechanisms that people have used for crowdsourcing, which are reputation, altruism, competition, curiosity. So we basically chose to investigate what can these incentives give you, right, in some sense. So for this particular game, what we tried to concentrate on is the reputation competition incentive, right, where we said that now when you play this game, you can see your rank in the context of your friends or in the context of the general population, right? And that sort of worked for us. So we went through different design iterations, but this sort of worked really well. The friend ranking and the everyone ranking, because it sort of motivated people to sort of play well. Okay, so I'll not give you the demo, but you can try it out on Facebook if you have an account. So this was released in end of September in 2010, and actually last year, 2011. So we have got till now we have got 2,800 users, around 6,000 games, and then we basically did a analysis with only a subset of the data with 662 users, 1,883 games, and in these 1,883 games, 524 were played against friends, played between friends. 332 were played between strangers, and then 1,027 were played in the setting where one of the opponent challenges somebody random who he doesn't know who is he challenging, right? But the other person knows where the challenge is coming from, right? So it's a asymmetric game in the last setting, and this is sort of the demographics. So this is sort of typical of. So essentially, when I started the analysis, we were at week 4, but I mean, we are in the process of doing a more thorough analysis, trying to get into learning effects where we are going to analyze the whole data, right? So this is like yeah.
Did you encounter any policy manipulations where I create a fake account and I play against it continuously to just increase my rating?
Yeah, so basically, so that's a very good question. We didn't encounter it, but
one thing that was close though.
yeah,
One guy that created bots to play the game. He was pretty honest about it. So we saw a bunch of games initiated suddenly across the board. So 1,000 games within 1 hour, and we got an email from the guy saying a bunch of questions about the game. And then we sort of said, listen, you know, it's a scientific experiment, please back off. We'd love to chat about the game. We're in touch, but we didn't want them contaminating the data. That's obviously a problem with these kind of settings. Although it wasn't for money or anything, right?
Yeah. Yeah. So if you look at the demographics, I mean, it's this fairly standard, but that you would expect. The population was predominantly male, and it was predominantly sort of young, and then it was coming from like a variety of different countries, from the United States, from the United Kingdom, a lot of people from Egypt, Spain, India, Saudi Arabia, and then among the towns and cities, I don't understand why we got so many people from Riyadh, but I guess they are really interested in game theory. So I mean, now I'll basically try to sort of relate our work to the conventional analysis that people had done before on this game. So now the first thing that people sort of do is to look at the troop distribution, right? How many times a particular size of troop, a troop set was used, right? So recall that the theoretical analysis, right, the optimal sort of mixed strategy said that essentially all the troops, there should be a uniform distribution among the troops in this sort of range between 0 and 40, right? That is what the theoretical prediction or the optimal mixed strategy is for this game. And we see that yes, of course, after 40 there are people who are playing troop sizes which are more than 40, but it is really small, right? It really goes down quite quickly, right? So this is generally the most popular strategies that were used. So this is the dumb strategy where you are guaranteed not to win. Surprisingly, 67. This was played 67 number of times, and then this is the first level strategy where you think, okay, I'll just distribute them uniformly. So this was a very popular strategy. Now this strategy is generally beaten by this strategy where you try to reinforce 4 cities. You say, okay, I'll reinforce 4 cities and then put a 0 here, right? So this was also popular. And then this is the third level of reasoning where you say, okay, I want to win 3 cities, and therefore I'll just concentrate all my troops in just 3 cities, right? 33, 33, 34, right? And then there were a mix of other strategies which were sort of trying to basically beat the other strategies. So this is a graph which actually gives the insight about what strategy was being used and what were the domination relationships. So the size of the circle here in this graph shows the number of people. The area of the circle is proportional to the number of people who played that strategy, right? So 2020, the uniform strategy was played by a lot of users, right? This strategy is in turn beaten by our 34-33-33 strategy even if you sort of permute the distribution randomly, right? You're guaranteed that this strategy sort of wins against this strategy, right?
What happens with ties?
So in ties, basically both players get a single point.
So they win. So ties counted as a win.
No, half. They share the win.
Okay.
Yeah, they share the points, right? So in Blotto, you have these circular domination relationships where a strategy beats another strategy, this strategy beats this strategy, and then this strategy beats this strategy, right? So you have these circular domination relationships which are similar to rock, paper, scissors, but in a much more complicated space, right? And then you can ask the question now, what is the best, given this graph, what is the best strategy to use? Now, the best strategy to use is not the strategy which beats most number of strategies. It's the strategy which beats the majority of the people, right? The majorities of the distribution. So you really have to see that you want to beat these big circles, right? You want to beat this, you want to beat this, you want to beat this, right?
But what happens, so how do you compare, for example, 34, 33, 33, and 33, 33, 33, 1? So it would seem to me that both sides have 2 ties and 2 wins. I mean, 1 win, 1 loss, right? So
Yeah, so
who wins in that battle?
so they will both tie, right? So in this case,
So this guy versus
this guy. So there is a 0.6 probability that this guy is going to beat this guy. So if you basically,
If you want, assuming you want to
yeah. Okay. Okay. How much time? Okay, 10 minutes left. Okay, so I have to quickly go through it. So this is the strategy that basically performed the best, right? But if you go and play the game now, it would have changed because people continuously evolve their strategies in some sense, right? So the 3-week threshold, this is what was the top performing strategy at 3-week mark, right? But it has changed since. So we also wanted to study the effect of biases, social habitats, and the knowledge of the opponent, right? Because this is something that previous studies had not been able to explore. So when you bring in subjects to the lab to conduct these experiments, you don't really know the relationships between these subjects, right? Whether they are friends, whether they know each other, what sort of information they are using to play against the player. So the first thing that you can sort of analyze, and this is something which is conventional in the literature, is to just look at the mean value of the different distributions in different fields, and you would expect that this is uniform, right? But this is not. Like if you and these differences are really significant, right? So you see that there is this sort of a distribution where the central sort of the battlefields get more troops, right? And this is sort of a framing effect in some sense, right? That just because we had shown that different battlefields are in this order, people tend to concentrate their troop distribution in the center for some strange reason, right? But you can exploit that now if you know this distribution. And this is not just true for all particular strategies, but it's also true if you look at specific types of games. So if you see games played against the hidden player, against strangers, against friends, you see that this persists in all these different types of games. Yes, David?
There were numbers given for the battlefield, so I saw which one was which number.
So essentially, you saw so this is essentially what was given, right? So these were the different allocations. These were the different positions of the battlefields, and the users were essentially saying, okay, this is how much I will basically.
Did you ever sort of rearrange the geographically out, for instance, arrange them in a circle so that there's no line in the center?
Yeah, so we were planning to do this at some point of time, and we were even planning to do the first thing that we actually planned was to use a real world map, but then we thought, okay, that would introduce a lot of a big framing bias, right, in the game. So these are things that you have to consider, that these framing effects might bias your results, absolutely. But we didn't try that study out, try that thing out. Yeah, but it would be interesting to sort of look at that. So now this is something interesting. So in one of our analysis, what we did is we looked at when people initiate games against friends, against strangers, and against hidden players, what is their probability of winning, right? And you see that when they initiate the game against friends, they are more likely to win, versus when they initiate the game against strangers. And when they initiate a game against a player they don't really know about, then they don't even know the name of the person or the ranking of that person, then they really don't perform well, right? So in this case, they knew who they were sort of challenging. They could see the name, they could see the rank, and in this case, they actually knew the person. This person was on their friend list, the Facebook friend list. And in this case, they didn't know anything. And then you see that there is a significant difference in the winning rate. And this is something which is the effect of experience. So now if you look at how many, yes?
Are you going to show us this when you control for experience? I mean, when I initiate a game against a friend, there's a much higher chance that that's just a friend, they haven't played it, whereas if I play against a hidden player, that must be someone who wants to play the game.
So that is true. That is true. So basically so
You're just revealing experience.
yeah. So you can make that claim between this and this, but between these and these, they are in the same setting, right? The strangers and the hidden. For example, strangers and hidden are taken from the same population, which have already played one game, right? And then somebody says, I'll challenge this particular player, and then they say, okay, I'll challenge somebody who at random, right? And in that case, you still see that there's a big sort of jump. There's a 10% sort of difference in probability, but you're absolutely right that we should control for the effect of experience in these sort of results. And this is the effect of experience essentially. So as the number of games played increases, your winning rate increases. Now this could be because of two reasons, right? One reason is that really the people who win a lot, they essentially tend to persist in the game, right? They really play a lot of games, or as they play a lot of games, they get more information about the strategy, and therefore they win a lot, right? So there are two factors which we have to isolate in some sense. Yes.
So this sort of, I might have missed this
Mhm.
when I was out, but one would have thought that a very simple question here would be that if you play the game again and again,
Yeah.
you essentially learn how to play it.
Mm-hmm.
So is there, do you have results about experience? So you have two players who are experienced.
So this is one of the things that.
Basically, you know,
Yes. So this is one of the things that we want to do, is not just look at how people's strategy is evolving over time, but also look at what influence the network has. So if the player has played a game, if somebody is constantly playing games against a highly ranked opponent, right, and he's basically getting beaten by, he's getting access to some very advanced strategies, right, or distributions, then maybe he's learning a lot faster. Right. So we really want to control for that as well in some sense, the network effects, and then sort of do the learning, right? Because if you just do the learning without ignoring the network effects, then we might not get a reasonable answer, right? So that is something that we are looking at the moment. So I have 5 minutes left, so I'll basically quickly go through the challenges and limitations, and then tell you something completely different. So there are a lot of limitations of this work, right? We used the reputation and competition sort of incentive, but one may argue that the users may not play the game seriously, right? They might affect biases. Of course, there are framing effects that directly come from the design of the game interface, right? And then the last point, which is our original motivation, which was the subject bias, right? The subject bias does not go away completely, right? Because the people who are coming in to play these games, they are interested in maybe playing these types of games. So there is a bias there, right? We are not getting subjects from the general population in some sense. So there are some limitations which you have to think about. Now, we did this study for behavioral game theory, but we have been also looking at other sort of situations. So one particular area that we are interested in is trying to use crowdsourcing with different incentives for training machine learning systems. For example, suppose you want to train a system for suppose you want to train a search engine, right? What do you need for it? You need pairs of inputs, which are say the query, and output, which is a ranked list, right? And you want to see what sort of people like what sort of outputs for the search problem, right? So this is one setting that we were interested in, and the way we looked at this problem is by asking the question: can you sort of infer the preferences or the personality of Facebook users by just looking at their profile information or the types of websites they liked, right? So this is joint work with a lot of people, and I don't have time to actually go through the work. I'll just tell you something about this work to summarize this work. So David Stillman and Michal Konstanski were students in the Psychometric Center, and they released this Facebook app, right, called My Personality in 2007. And Michal did an internship with me in 2009, and when they released this app, they were hoping that a few hundred people or maybe 1,000 people would sort of take the test, and we would get personality scores from this app, right? So that once you get the personality scores and you have the set of likes or this their Facebook profile characteristics, then you can sort of do some sort of correlations or try to predict one from the other, right? Now, up till now, this app has been used by 6.5 million users, right? And the incentive is nothing but curiosity. People are just interested in using this app just because they want to know their personality scores, right? So, and there are some very interesting results that I can sort of show you. We can ask the question now: what is the personality of people who like Netflix or the Pirate Bay, which is sort of illegal sharing website, and you can find out that the people who are using Netflix are cautious people, and the people who are using Pirate Bay are sort of curious people. And then you can also do organized versus careless, shy versus outgoing, competitive versus cooperative, and young versus old, male versus female, right? So Pirate Bay are more male. And you can do the same thing with universities, and now you can see that Harvard is sort of liked by people who are older for some sense compared to UCLA or Cornell. So I'll just conclude by saying that there is a big opportunity in basically using these incentives to get a lot of interesting data out from these systems. But the big challenge here is how do you incentivize the desired behavior, right? The behavior that you really want without biasing the results. So with that, I'll stop.
Are there any questions? Yes.
So, are you familiar with the work of Sam Gosling at University of Texas?
Yeah. Yeah, absolutely, absolutely. So Sam has been working on personality stuff. Yes.
So, how does your work differ?
So Sam has been used. I don't know if Sam used Michal's data.
No, I mean, we talked to Sam through emails when we did this work. So one key difference is we actually looked at items that were liked in Facebook as opposed to a lot of his work, which is high-level. Another difference is that in a lot of the work he's
Yep.
Yes.
So you call this the effect that, depending on how you lay out the choices in the interface, that has an effect on how users play. Called the framing effect, I think. Perhaps not the best wording for it, something like positional effects. I think it's used in psychology.
Mm-hmm.
And you listed this under challenges or complications.
Mm-hmm.
I think this could also go on the page where you say this is a big opportunity actually to explore this question. So people in marketing or in interface design are very interested in what's the effect of laying out the choices on how users behave.
Yeah, I think basically you're absolutely right. There are you can look at this problem in both from both sort of perspectives, right? If somebody does not want to investigate these positional effects, then it's sort of a nuisance for them, right? But if somebody really wants to see how people's attention is sort of grabbed, or how do they actually distribute the troops, and if I can sort of exploit that while designing the game, or in fact even playing the game, then yes, of course. I mean, if I'm sort of a person who wants to beat other people, I want to design a strategy, then I'll probably be interested in finding the positions which have the biggest positional bias, right? Because then I can exploit it, right? So you're absolutely right. There is, it's like it's two sides of the same coin. Yeah.
Yes.
What is the desired behavior? Is it just honest behavior?
Yeah, so that's also a very subjective question, right? That totally depends on what you're interested in, and that is related to the question that was asked right now, which was about the positional bias, right? You might be interested in investigating the positional bias, right? So the desired behavior. So suppose if you are interested in finding out how people sort of play the game in India, right? So that is the desired behavior. Then like getting all subjects from India would not be a bias in your data, right? So it's about, you have a context in mind in which you want to sort of deploy the system, or you want to learn the behavior of the users, and that is what you want from in the experiments, right? That's what you want to come out. The behavior should match the behavior that you would sort of that you would expect to see at deployment time, in some sense.
I think we stop because we have one more talk to go.
Yeah.
Thank you very much.